This is the final video. We're there, the final video from the Edexcel GCSE in Astronomy, topic 16, all about cosmology. It's been a long road, but we're nearly there. So, this is the specification. Feel free to have a look at that. This is what we're covering in this video in some sort of order. We're going to start with spectrometry. If you're going to do any sort of investigation in cosmology, you've got to start with how you get information from the cosmos. So the diagram you can see on the top here, what we've got is a lamp, a slit and a prism. That's what we've got. This is just a slit cut into a piece of card, and that's just a lump of glass shaped like a triangular prism. Now the lamp gives out light. It looks white. The light passes through a slit, which then passes through the prism. And because of the angular shape of the prism, when we get refraction from both surfaces, the incoming surface and the surface when the light comes out, the refraction is going to push the light away from the normal across both of those boundaries. Now, it turns out that visible light is refracted by slightly different amounts for different colours. So red actually refracts less than blue light. The blue light actually travels slightly slower through glass than the red light does. It's only a small amount, but it's enough that if you do pass white light through a prism, it will split into the different colours. We call that effect dispersion. And if you look at the spectrum through a prism, this is difficult to see from this picture, but that is actually a glass prism that we're looking at here. If we look at an old style incandescent lamp, which has a filament of tungsten which is glowing white hot, then you can see a continuous spectrum of colours. If we use our energy saving lamp, which has a mercury vapour which is glowing, and then the inside of the lamp is coated in a white fluorescent powder which glows in different colours when it's excited by the ultraviolet, that's what we see, discrete colours, which your brain interprets as white. Now this is going to be our main tool for investigating anything to do with the cosmos. We're going to take light from a star and send it through a spectrometer. Now modern spectrometers don't use prisms for various reasons. They use diffraction gratings, and there are different types of spectrometers. Some use transmission diffraction gratings, some use reflection diffraction gratings. It doesn't matter. It really doesn't matter. It's not a physics course, it's an astronomy course. So diffraction is the preferred method for getting these different colours of lines. In a spectrometer, you can very precisely measure the wavelength of those colours. And based on that wavelength, you can determine the energy of the particles. I don't want to call them particles, the quantized energy of the photons that are moving through space that we call light or electromagnetic radiation. So that's going to be our main tool. We can use this for all sorts of wonderful purposes, and I did put a video on my channel not too long ago where I used a spectrometer when I was investigating the photoelectric effect, just because I needed to know what the wavelength of light was that was transmitted through a set of filters. So I got the spectrometer out to measure that. So that's, you know, a useful thing that you can do with this. But there we go. Let's move on. We can get a continuous spectrum. From some bodies we get a continuous spectrum. Why do we get a continuous spectrum? Because everything emits radiation, electromagnetic radiation, if its temperature is above absolute zero, 0 Kelvin, negative 273.15 degrees Celsius. Everything emits radiation. Now, cold things emit infrared radiation. The higher the temperature of the body, the further up the electromagnetic spectrum we go. So if you get something to a temperature of about 3000 Kelvin, as you can see here on this graph, it's emitting infrared. This is the region of the graph with wavelengths in the infrared area, but it's also emitting a bit of red and a little bit of the other colours, but mostly red. So something that is red hot is going to be around about 3000 Kelvin in temperature. This peak starts shifting towards the orange and then ultimately right into the middle, so we're getting as much blue as we are red coming out at the higher temperatures. By the time we get to 6000 Kelvin, something appears white hot. And if you continue to increase the temperature of the body, eventually you're getting more blue light emitted than red light, and the body will look blue, which is why hotter stars are blue, whereas cooler stars are red. And the very hottest, the very highest temperature bodies in our universe, active galactic nuclei and the region around them, they can be emitting right into the X-ray region of the electromagnetic spectrum. And I won't say gamma ray because nuclear reactions are required for gamma radiation, but we are getting nuclear reactions happening in that region around active galactic nuclei, so maybe saying gamma radiation is perfectly appropriate. Let's ignore where it says classical theory here. This is a standard diagram that's used when we talk about the ultraviolet catastrophe, and if you're interested in physics, go ahead and look that up. It's an interesting part of our physics history, but not for today. We're looking at cosmology today. So the first bit of information that we can get through spectrometry, just looking at the colours of radiation that we're getting, is we can estimate the temperature of whatever it is we are looking at through our spectrometer. Well, that's fine, but we can get more information than that. Because it turns out when you look at the absorption, when you look at the shouldn't say absorption, not yet. When you look at the spectrum of radiation emitted from things like the sun, the atmosphere of the sun absorbs some of the colours of radiation. And we get what's called an absorption spectrum. And you can look up the absorption spectrum for the sun if you like, but this is a hugely simplified version of the absorption spectrum of the sun. This is what a continuous spectrum would look like, but actually from the sun we get dark lines. That is, colours that are not as bright as the colours around them, because some of the radiation of those particular colours has been absorbed. Now, we can think of light as a stream of energetic photons, where the energy of each photon is directly proportional to the frequency and therefore inversely proportional to the wavelength of the electromagnetic radiation. Photons of red light each carry less energy than photons of blue light, because blue is a higher frequency and a lower wavelength than red. So that's kind of how that works. So we've got certain colours missing from the light we get from the sun, and therefore there's certain energies of photons that don't make it out of the sun. They're absorbed in the atmosphere of the sun. And what we can do on Earth is we can take a bunch of gases and we can excite those gases, heat them up maybe, or some other method of exciting them, and they glow. And we can look at the spectrum that is emitted by a hot gas, and that's called the emission spectrum. Now, would you believe it? From the sun, those dark lines correspond to the light lines that you get when you excite hydrogen. Now, what that means is that hydrogen, when it's hot, will emit these colours. Well, if everything's hot, then the hydrogen, even hot hydrogen is going to also absorb these colours. So if everything's hot and we've got a huge amount of what we call black body radiation, that's that continuous spectrum that's emitted from all bodies at a temperature above absolute zero. If we get loads of that continuous spectrum radiation, then the fact that some of the light that is emitted by hydrogen when it's hot is also absorbed by hydrogen, means we're going to end up with dark lines. They're not actually black, but they're going to be less bright than the lines around them, indicating that that light is absorbed. So that is a fingerprint, if you like, a fingerprint that we can use to determine what the composition is of whatever we're looking at through our telescope. We just take the light from that telescope, run it through a spectrometer and see what is absorbed. And then look in our big catalogue of emission spectrums and match them up. It turns out that, lovely story from history, there was one particular absorption line from the sun that scientists could not explain when it was first discovered. I forget the details, so some of this is apocryphal, but there was a particular colour of yellow, and there wasn't an element on Earth that had an emission spectrum that corresponded to it. So a new element was invented called helium, helios being the Greek word for the sun, helium, which was an element that was discovered and thought to be in the sun, but not here on Earth. And then, of course, we discovered helium on the Earth later, found this gas, got it excited, it glowed with the particular colours that we were missing from our absorption spectrum of the sun, so we'd already named the thing, and we named it from looking at the sun before we found the stuff on Earth. I always find that an interesting story. So that is what we can do with an absorption spectrum. Now, one of the things that's interesting is when you look at the absorption spectrum from very distant stars, and by very distant stars, I mean stars that are in distant galaxies. When you look at them, in those cases, we get the same sort of fingerprint, the same relative spacing between the dark lines, but the whole thing is shifted towards larger wavelengths. All the wavelengths are increased a bit. And it turns out the more distant a galaxy is, the more the increase in wavelength of the dark lines that would correspond to the absorption lines for hydrogen. And we know they would correspond because the relative spacing of those lines. So we call this effect redshift. Now, how does redshift work? There's some quite bad physics coming up here, I'm afraid, but it is something that you need to learn for your Edexcel your Edexcel GCSE in astronomy. So my apologies for the bad physics for those maybe A-level students or even undergraduate students who are watching this and thinking, well, he's just said something wrong. I know, I don't have much choice. So let's talk about redshift and blue shift. The standard argument that is given is that it is a Doppler shift. As stars move away from us, the light is increased in wavelength. When stars move towards us, the light is decreased in wavelength. And that's okay. I don't mind that. So far, that's okay. The Doppler shift, what we could say here, is the idea that if a body is moving relative to an observer, then the waves are going to get squashed in the direction the body is moving and stretched out in the direction, the opposite direction to the direction the body is moving. So if I'm an observer over here on the right where my cursor is, then I'm going to see the wavelengths being a bit smaller. And so if I'm over here, then I'm going to see the wavelengths being a little bit bigger. And the rationale is that as this red dot, which is emitting these waves, is moving, each wave it emits forms a circular wave front, but by the time the next wave front comes along, the emitter has moved a bit. It kind of makes sense. It kind of makes sense when you think about it. It's compared to the Doppler effect for sound. And this is where I have some issues with this. It's compared to the Doppler effect for sound. The way the Doppler effect for sound works is that if an ambulance is moving towards you, you would hear the siren in a higher pitch, and as an ambulance moves away from you, you hear the sound in a lower pitch. And you could have, a racing car go past, and everyone knows the sound it makes. Yow! Okay, it's high pitch, and then low pitch. Wah! It's yow! Like that. It's decreasing in wavelength as it goes past us. I'm so sorry. So, why does that happen? Well, this is the problem now, isn't it? It happens because as the object is moving towards us and emitting its waves in front of it, it's kind of catching up with its wavefront a bit. And you can see that from this animation. It's kind of catching up with its wavefront a bit as it's moving. If the red blob was moving fast enough, it could even overtake the wavefronts. Well, if this is sound, where the wavefronts are all bunched together, that's actually going to increase the amplitude there. And it's going to become harder and harder to get faster and faster. And that's the barrier to getting faster than the speed of sound. And it was discovered with airplanes. If you make the airplane shaped like an arrow so it can pierce through that high pressure barrier, then you can get airplanes to go faster than the speed of sound. And some aircraft are very clever. They have wings that can fold back to make them pointier as they approach the speed of sound. So they can end up going faster. And that's where the intelligent people are going to be thinking, hang on, Keith, you can't go faster than the speed of light. The speed of light from the moving observer, in this case the red dot, would appear to be the same going away from the observer as the speed of light observed from someone who is not moving, who thinks the object is moving. It all agree on the speed of light. And what that means is that relativistic redshift is a lot more complicated because of the invariance of the speed of light in a vacuum. So I'm sorry, I'm going to have to use the Doppler shift equation argument here. It's a little bit naff, it's a little bit weak, but this is what we have to do. So let us do some derivations. Let's first of all assume that the wave that is being emitted from, in this case it's light, so it's emitted from a star or galaxy, is emitted, let's say, with a wavelength of lambda 0. And lambda 0 could actually be just the dark line, the wavelength corresponding to the dark line. It doesn't matter. Or it could be the light next to the dark line if you want to visualize it as light. It doesn't matter. The detected wave has a larger wavelength. It's been stretched out if the object is moving away from us. And the difference in those two wavelengths, lambda 0 and lambda, we can call delta lambda. Now the distance that the light will travel during one time period is called the wavelength. So the distance that the wave will travel in one period, which is what we call capital T, a time period, the speed of light is c, and we end up with this top equation there. An observer, sorry about this, an observer moving with a velocity v for the same amount of time, let's say that it would travel a distance delta v, okay, delta lambda, sorry. That's the distance that an observer is going to travel in one time period. Fine, okay. If I do the ratio of these two, the t's cancel, and delta v is just the difference between them, and I get this equation here. I mean, it is what it is. You don't have to like it, but it is what it is. I've got a bit of an animation here just to try to help you see what's going on. I don't know if this is helpful. Yeah. Is that helpful or not? I don't know. Oop, let's go forward again. I'm slipping through my slides too quickly. Is there a better derivation? Well, maybe. And I'm just going to flash this up here for a second, just because this is fun. This equation here is your length contraction equation based on special relativity. Below that here, we've got what happens when we square that equation, then multiply it out, and you can follow the maths here. We've multiplied it out, and then we are subtracting x0 squared from both sides, and then we're dividing through by x0 squared as well. We end up with an equation that looks a bit like this when we multiply through by -1 as well, so these two swap over. And if the distance we're talking about is a wavelength, we get something that looks a bit like this. But when you look closely at this, you'll think, well, it has similarities with the Doppler shift. But it is not the same. I'm going to leave that for you to think about, to ponder on. You can't use special relativity like this to get to a nice equation for redshift. And the equation we've got for redshift here is just a first order approximation. It's not very good. But it is GCSE level. And according to the specification, it says, get the exact wording here, be able to use the formula. So you don't need to memorize it, you just need to be able to use that formula. You know, how good that formula is, that's another story. Right, let's carry on with redshift. So here we've got an analogy. It's got some flaws, but there's bits in it that kind of work. Imagine you've got some raisin bread, so that's bread, it's got raisins in it. And as the raisin bread inflates, it's going to inflate because it's got yeast in it. That's kind of what bread does. As it inflates, the raisins are all going to move apart, or appear to move apart. Fine. If we say that the nearby raisins have moved from being 5 centimetres apart to 10 centimetres apart, then the nearby raisins have moved a total distance of 5 centimetres. In the same amount of time, there are farther raisins that started at 10 centimetres apart that end up at 20 centimetres apart. So they have moved 10 centimetres in the same amount of time relative to this first raisin, the primordial raisin, I don't know what you want to call that sort of thing. This raisin that's sort of in the centre here somewhere, there it is. So as the universe expands, farther stars will appear to move faster because they appear to move further in the same amount of time. It's not perfect, but it'll do. It's a raisin bread analogy, it'll do. Now, if you look at the recessional velocity of galaxies, which you can use that redshift equation to determine, that's the velocity that galaxies recede away from us, and you plot that against the distance to those galaxies, you get something that looks like a pretty good straight line. I mean, how do we measure the distance to these galaxies? There's a few ways of measuring it. If they're nearby galaxies, we can use parallax. As the Earth moves around its orbit around the Sun, we can use the parallax angle for those galaxies to calculate the distance to them. The parallax angle becomes too small with distant galaxies. The other thing is we've got stars called Cepheid variables, which have a particular frequency which is related very strongly to their brightness, their absolute magnitude. And we can measure the apparent magnitude, and we did that in a previous session. Measuring the apparent magnitude and knowing what the absolute magnitude should be and using that to determine the distance. So there are ways with galaxies of determining the distance to it, and then we get this really lovely straight line. This is called Hubble's law, this straight line. The direct proportionality. V, the recessional velocity, is directly proportional to d, the distance to that galaxy from us. And because it's a straight line, the constant of proportionality h0, Hubble's constant, is a constant. Now, in terms of what that constant means, what is it equal to? We've got a number here, about 71 kilometers per second per megaparsec. And I think I've talked about what parsecs were in a video a while ago now. Parsecs being a tremendously big unit of distance, and I've written the conversion down there as well. But what does it physically mean? What's the physical significance of that Hubble's constant? Well, let's have a look at the dimensions. A-level students are going to like dimensions. GCSE students might not have seen this before. But where I've got square brackets, I'm putting what type of measurement it is. So kilometres is a unit for a length measurement, and I'm using a capital L for that. And kilometres there, seconds is on the denominator. It's kilometres per second per megaparsec. Seconds is a time unit, and megaparsecs is a distance unit, and the distance unit on the top cancels with the distance dimension, we call it, on the top cancels with the distance dimension on the bottom. So kilometres per second per megaparsec, which is what this unit is, that is a reciprocal of a time. So the reciprocal of that unit, okay, the reciprocal of this unit would be a time. It wouldn't be in seconds, because we've got kilometres here and megaparsecs there, but we could convert it. So the reciprocal of 71 kilometres per second per megaparsec is 1.408 times 10 to the negative 2 seconds megaparsecs per kilometre. So you can see it's just the reciprocal. This is the reciprocal of this. And it's an amount of time. And if we do a conversion, because we know how many kilometres per megaparsec, and we've got here megaparsecs per kilometre, so the units kilometres will cancel, and the units megaparsecs will cancel, just by timesing by this conversion. So if we do that, we end up with a time in seconds. And it's a big time, 4.346 times 10 to the 17 seconds. It's a big time. 10 to the power of 17. That is phenomenal. But we can convert that into more understandable units, and we end up with about 13.8 billion years. Well, that was with a too significant figure, Hubble constant of 71, so rounded to 14 billion years. If you use a better Hubble constant, you get closer to 13.7 billion years rather than 13.8. They're just rounding errors because of the numbers I chose to use. But it's close. No, 13.7 billion years. What's the physical significance of 13.7 billion years? Well, speed is distance divided by time, or duration of movement, as I've called it here. So the duration of movement is the total distance travelled divided by the speed they travel. So if all the galaxies are moving away from us, and they've been moving for the same amount of time, and they've travelled a distance equal to their distance away from us, then they were all here at this point in space that amount of time ago. 13.7 billion years ago. If in 13.7 billion years, travelling at such a speed, they've moved away from us, and they're all moving away from us, they've moved away from us by such a distance, then that long ago they were here, which means that we are the centre of the universe, but so is everywhere else. Everywhere is the centre of the universe by this logic. In the same way as we've got our expanding raisin bread. Remember our expanding raisin bread? You can sort of shrink it down and imagine it's all in the same place. But actually, it's not, is it? It's not all in the same place. There is no point when you're making bread where it's a singularity of bread. So, you've got to be cautious about how you interpret Hubble's constant, but it gives us a number which is an estimate of the age of the universe. Or does it? Because there are other theories, or should I say other hypotheses, rather than saying theories, other hypotheses. So this is one idea, is that the universe persists in a steady state. As the universe expands, and you can see that indication here, the red and the green dot are moving further and further apart on this picture, and if you have red-green colour blindness, I apologise, this isn't going to make a tremendous amount of sense to you. I'll move the cursor over the red dot here, then the red dot there, then the red dot there, and I'll do it over the green dot here, then the green dot there, then the green dot there. So hopefully you can sort of track what would be happening. You would still see stars and galaxies moving apart, but new matter would be placed in the middle, created, produced, coming into existence in between galaxies. That would still allow us to have this redshift, because there would still be galaxies moving apart from us. That would still allow redshift, we'd still see expansion of the universe, but it would mean that the density of the universe would be constant. Well, why don't we think that's right then? And it's because of this. Quasars. There's two other reasons. There's three reasons. Quasars, cosmic microwave background radiation, and what we call Hubble deep field images. And they're all quite related, actually. The Hubble deep field images are related to the others. But let's go with quasars to start with. Okay, quasars. We don't see quasars nearby. We only see them far away. If the universe is in a steady state, then why were the conditions necessary for quasars around in the past and not now? That doesn't make any sense. So in order to get these quasars, you need to have had a much more dense universe in order to form them. And now the universe is that much less dense, they don't form. So that contradicts steady state theory. I'm just going to show you that beautiful picture of a quasar again. Again, it's an artist impression. It's on Wikipedia. It's on Creative Commons. But the artist, I need to look up who it is and send them some kudos, because that is a lovely picture. Cosmic microwave background radiation. What is it? Well, the Big Bang Theory predicts an incredibly hot, dense universe. If you're too dense, then light can't pass through you. If the universe is too dense, light cannot pass through it. But as it spreads out, it becomes sparse enough that light can penetrate through the universe. It becomes transparent. And you can predict the temperature that the universe would have to be when that happens, and therefore the wavelength of radiation that would be emitted. It would be very high energy radiation, yes. But redshifted over 13.7 billion years of universal expansion, and it would be shifted right the way down into the microwave region. And that is exactly what we observe. We observe cosmic microwave background radiation. It's as simple as that. The steady state theory can't predict the existence of this type of radiation. There's a beautiful picture of cosmic microwave background radiation map, zoomed nicely in so you can see it. And the last one, Hubble deep field images. So you look at the sky, you see stars, but to an astronomer who's interested in the very farthest parts of the universe, stars are a nuisance. They're nearby and they get in the way. But you can find small patches of sky between the stars where there isn't that much in between us and the farthest depths of space. The problem is that the light that might be emitted from galaxies that far away is so dim that our telescopes would not be able to, well, I certainly can't detect it. Our telescopes wouldn't be any good unless we continually collect a lot of light over a long period of time. And by a long period of time, I'm talking about days, weeks, months. So one of the problems here is that the Earth rotates. So if I've got a telescope pointed at a patch of sky, I'd have to rotate the telescope, constantly tracking that patch of sky. And then this Earth's going to rotate, so the sun's going to come up, and that's going to rather ruin my images. But I can just switch it off, then switch it back on again later, I suppose. But then you've got the turbulence in the atmosphere because the morning sun warms the air up and we start to see shimmering atmosphere. This is not going to work. So we couldn't get these deep field images until we were able to put telescopes in space above the atmosphere so that the atmosphere didn't get in the way and so that we could leave the exposure times to collect, for really long times, to collect loads and loads of light. So Hubble deep field images show huge numbers of distant galaxies, but they are much more dense than they are now. You can't help but notice that when you look at these images, these far field images. Not only that, the galaxies are incredibly redshifted, which means that they are incredibly far away and yet close together. If we were in a solid state situation, then we'd look up the sky and see loads of galaxies. We don't see that. We don't see that because of the universe spreading out. It's fun to imagine that there might be some intelligent race of aliens that lived on some planet around some star around one of these galaxies some great distance ago in past, who had all these galaxies that they could see in the night sky, motivating them to explore the universe, billions of years ago, and the cosmic time has had its way with that race, and maybe they're still around and maybe they're not, it doesn't matter. And now there's us, a bunch of apes on this rock looking up, and if we're lucky we get to see Andromeda with the naked eye as a teeny tiny fuzzy dot on a really dark night sky, and we get all excited about seeing that we're in the Milky Way. It's sad, isn't it? We're a sad species. Right, so Cosmic microwave background radiation isn't uniform. We discussed this before. It's not uniform. And we know that the galaxy density is higher where the cosmic microwave background radiation is more dense. But why? What's going on? I mean, maybe where it was hotter is where it was emitting more radiation, and then when it's stretched out, that's why it's the more intense microwave radiation. Well, that makes lots of sense. That makes lots of sense. Now, when cosmic microwave background radiation was first detected, it was detected almost uniform across the sky. This was back when we invented radar during the Second World War, and then we noticed this background microwave radiation, and we thought that was interesting. But it was a bit of a nuisance, and as we sent more and more sophisticated probes, more and more sophisticated, well, microwave telescopes really, up into space to get better and better images, what have we found? Well, we can see dark patch here, light, bright patch there, and then you go down here, dark patch, bright patch. The better our probes, the higher the resolution of the image we have got. So you can see here sort of 3 of them. We've gone a step beyond that now with the Planck mission. Here it is, the Planck mission, and you can see even higher resolution of the distribution. Now, if you think we're looking at tiny patches of sky and looking at galaxy distribution within those tiny patches of sky on our Hubble Deep Field images, it would be really helpful if we had an accurate view of what the intensity of cosmic microwave background radiation was in those regions of sky, so we could do a good comparison. So that's the purpose of these probes. What's interesting here is the last bullet point, the evidence that the universe is flat. And what we mean by flat is in a geometric sense. The universe is not curved, it's flat. It's Euclidean, not non-Euclidean. Now, you're going to have to look that up if you're interested in non-Euclidean geometry. It is interesting, and near masses, we have to consider non-Euclidean geometry. But on the larger scales, the universe is flat. That'll be important later, actually. Let's have a little think about dark matter. Can't get through a GCSE astronomy course without thinking about this stuff. What is it? Don't know. There we are, that was quick. But we do know a lot about it. Using our models of gravity, our most successful models of gravity, general relativity, incredibly successful models of gravity that can predict things that we've later observed, like gravitational lensing and the lack of existence of the planet Vulcan next to the Sun, which older models of gravity predicted that there was a planet there. There isn't. So using the most successful model of gravity we've got, galaxies with the amount of mass that we can see ought to be unstable. They should be flinging themselves apart. In order to have a stable galaxy rotating, it would have to rotate far slower. And you can see in this picture here, where there's not very much dark matter, which is indicated by purple in this particular animation. In order to keep it stable, it would have to rotate quite slowly. Galaxy actually rotates reasonably quickly, relatively quickly. Not that quick, but relatively quickly. We go around every 200 million years, so relatively quickly. Why wouldn't the galaxies all just be flung off into space? I mean, okay, they don't fly off. Of course they don't fly off. But the gravitational force would not be high enough to keep them in circular motion. And in their reference frame, you could describe a centrifugal force outwards. And I know some people are going to shout at me about that, but come at me. I'm happy to come at you with this. Centrifugal force is measurable in a non-inertial reference frame. I'm not wrong. So anyway, if the gravitational force isn't great enough, then the stars can't orbit, and they will therefore increase their radius, and they'll become disassociated with the galaxy. So that means there must be more mass in the galaxy than we can observe. But we can measure that mass, and we can, by looking at observations of the galaxy, we can map where this mass is, this missing mass. This missing mass we call dark matter. And it's all to do with galaxies clumping. And I'm not just talking about galaxies clumping together, but I'm talking about galaxies clumping with other galaxies in clusters and superclusters as well. It's dark matter which we can calculate how much there has to be to get what we observe in the night sky, what we observe based on our best models of gravity. Now, there are other alternative models of gravity that try to predict what we observe without needing dark matter. So far, those models have all fallen short. They've all been very easy to disprove. But that is not to say that there isn't a better model of gravity out there. We just haven't discovered yet. And if there is a better model of gravity out there we haven't discovered yet, maybe you'll discover it. It's very interesting. What we're talking about here is stuff we don't yet know. That's where you come in. But let's just go to the next slide then. Dark matter. Clusters galaxies together. Need it, because otherwise galaxies wouldn't cluster together. We know it's there because of observations of gravitational lensing. Light is bent by gravity, and the amount light is bent by is more than we would get if the only mass in the universe were the mass we could see. So there must be dark matter we can't see, dark matter. And cosmic microwave background radiation. Okay, so dark matter does not interact with radiation at all. It doesn't absorb it. It can deflect it gravitationally, but it doesn't absorb any. So this is how we can still observe the cosmic microwave background radiation from all different directions. Now, it might be that slight differences in the temperature in certain parts is because of this gravitational lensing of cosmic microwave background radiation. And there's work going on investigating exactly that. So what is dark matter? What do we know about it? We know that it affects gravity, gravitational fields. We know that. We know that it does not interact with electromagnetic radiation, therefore it's uncharged, it's neutral. We know that if it doesn't contain charge, it also doesn't contain what are called quarks, sometimes pronounced quarks, but I don't like that. Quarks, these are fundamental particles found within protons and neutrons, doesn't contain them because they're charged. We know that it's not neutrinos, they are uncharged particles as well, but they are very, very, very small mass, and the amount of dark matter we have, or we would need in order to get what we observe, is not is too much dark matter. Neutrinos are insufficient to explain that. Nowhere near enough. So we know that dark matter exists because it makes general relativity match observations. And you're going to say, well, hang on a minute, you said general relativity already matches our observations. Yes, it does, on certain scales, and it's the best model we've got. And this model also includes dark matter. It's called the CDM model, cold dark matter model of cosmology. And there's a slight modification to that called the lambda CDM model, but we'll talk about that later. So, actually, let's go on to lambda CDM now. And to talk about lambda CDM, we need to talk about dark energy. Do you remember this graph, Hubble's constant on the left? Yeah, it turns out that's not the full story. Sorry. If you look at even bigger distances, galaxies even farther away, it turns out that the line isn't straight. Whoops. So the universe expansion is not constant, which was an assumption that was made, which gave us a nice straight line. The universe expansion was different. The gradient over here, farther back in time, because it's a greater distance, the gradient was shallower. Whoops. On average. So, the thing about dark energy is it explains to us why the expansion of the universe in the past was slower than the expansion of the universe now. And that's not actually quite uniform, because you go back even further and it was rapid expansion, then it slowed down, then it sped up again. So it's not a straightforward thing. The more data we gather, the more we learn about it. But that's got nothing to do with dark matter. That's dark energy. Don't, just because they've both got the word dark in them, don't confuse them with each other. Nothing to do with each other. I mean, they both happen to be part of the lambda CDM model of cosmology, which is a part of general relativity, but they're not actually the same thing at all. Dark matter is, what I've already discussed. Dark energy we know even less about. Dark energy is a fudge factor. That's all it is. If we look at the lambda CDM model, and I've written lambda rather than using the Greek letter lambda, which just looks like a triangle. I can't remember why I did that. I think I was in a rush when I made these notes and I never got round to fixing it. Perhaps I should fix it now. Lambda CDM. So here is the lambda symbol, the Greek letter lambda, and Albert Einstein used the Greek letter lambda as the cosmological constant. The cosmological constant gives you some indication of dark energy. It's just how much dark energy there is in the universe. That's what the cosmological constant is. Albert Einstein initially said it was a blunder to include the cosmological constant. He was quite embarrassed about it, but it turns out that even though it was an accident, really, he shouldn't have included it, he said. It's a good job he did, because it fixes the cold dark matter cosmology of the universe. Lambda CDM matches observation. So the existence of dark matter, explaining the clumping, and the existence of dark energy, explaining the expansion accelerating, that's all covered by lambda CDM model, the lambda CDM model, and it matches observation, which is good. The problem is, detecting stuff is not that easy. Detecting dark matter, well, if it only interacts with gravity, then we can only detect it by what it does to things gravitationally. So it's gravitational lensing of light, and the way that orbital mechanics of different galaxies, although things move so slow in the larger scales that it's difficult to make those sorts of observations. And you can't do observations on the small scale because of how weak gravity is. We only very recently, as in the last year, managed to investigate whether anti-hydrogen falls down or up in Earth's gravitational field. It turns out that anti-hydrogen, that's an anti-electron known as a positron orbiting an anti-proton. It turns out it falls down. Thank goodness for that. That's what our theories predicted. Although it would be more interesting if it falls up, because then we'd have discovered anti-mass, and that's actually more interesting, because we need that for wormhole technology and warp drive and all the rest of it. Science fiction. So dark energy. The problem is, we predict it's very sparse, and how on earth do you detect it? We just don't even know. We've got no idea how to detect this stuff. Again, that's where you come in. We don't know. So now those two quantities, dark matter and dark energy, they're closely tied to the fate of the universe. A joke that annoys me. People say, well, don't trust atoms, they make up everything. It really bugs me, because it's just simply not true. And this pie chart here is also not true, because it has atoms 4.6%, but that's not true. Most of the matter, I'm not talking about dark energy or dark matter, I'm talking about regular matter in the universe, is found in stars, which is plasmas, so they're ions, not atoms, or in black holes, in which case, I don't know what we call that stuff, but certainly not in atoms. And of that normal, everyday, regular matter, which is only 4.6%, of the universe, so atoms make up the tiniest of tiny proportions of matter in the universe. But anyway, rant over. This is our best prediction based on observations that match lambda CDM model. These are the numbers that give us our observations. But we could be slightly wrong. There could be slightly more dark matter or slightly more dark energy than we have so far measured. And if there's slightly more dark matter, That means gravity is going to be that little bit stronger on the universe, and it could cause the universe to collapse down, and then we have an infinite series of universes, big crunch, then a big bang, then a big crunch, then a big bang, and so on. Alternatively, we could have a little bit more dark energy than dark matter, and in that case, rather than the expansion carrying on slowly forever and ever and ever, or even accelerating as it is, it could accelerate at such an amount that it's an observable ripping of the universe. It's which sounds terrifying. So this is a graph, and you can see average distance between galaxies on the y-axis. On the x-axis is time, and we are in the middle, 0 billion years from now. And you'll notice with that lovely straight line, we have 13.7 billion years. And actually, even with some of the curves, we still have 13.7 billion years. Our best prediction is this one here, where the omega m, so that gives you the density of dark matter, has that value, and omega lambda, that gives you the density of dark energy, has that value. That is our best prediction. It matches what we observe now. It also gives us a 13.7 billion years, not that we need it, and matches our observations of what we see at the farthest of distances. So it looks like we're heading for infinite expansion and heat death of the universe. That's what it looks like. So here's a two-dimensional graph, bit of a map, showing omega m and omega lambda on the x and y axis respectively, and you can see that if we add too much dark energy and not enough dark matter, there just wouldn't have been a Big Bang in the first place. The different models here have been ran with different amounts of dark energy and dark matter. You can see you've got acceleration of the universe up here, deceleration down there, and if we had exactly along this line the proportion, then we would have a universe which is not accelerating nor decelerating. And cosmic microwave background radiations give us an estimate somewhere in this region, and so on and so on, and different experiments. So, you can see galaxy clusters give us this much dark matter we ought to have, this density of dark matter, with no indication of dark energy from what we get from galaxies. And so all different experiments also coincide around these values, about 0.7 on dark energy and about 0.3 on dark matter. And that's why we are sort of, we reckon we're pretty sure that that's what's going on. Future of the universe. This is a log graph, a logarithmic x-axis. So we're right the way down here somewhere, 10 billion on the logarithmic axis. Well, 1 billion is 9, so 10 billion would be 10. So we're on about 10 on this log axis. 13.8 billion is just a little bit more than 10 on this log axis. That's where we are. And then the last star has died. That doesn't look that far away from where we are now. That looks quite scary. But it's a log scale. That's a long way away. And then if we carry on looking along here, we've got the last supermassive black holes have evaporated. Yeah, black holes evaporate. The smaller they are, the faster they evaporate. But given enough time, even the supermassive ones can evaporate eventually. And then just a lot of nothing, a lot of nothing, a lot of nothing, and then heat death. We're right the way back here. But it's a logarithmic scale. We've got a long time before oblivion. So, no nightmares. And that's it. That's how we finish. Congratulations. If you have sat there and you have sat through all of the GCSE astronomy videos, you deserve a medal. Well done to you. I need to go back and re-record certain parts where there are mistakes that have been identified since I've published them. That's fine, mistakes happen. Everyone makes mistakes, and I'm very grateful to people who pointed them out. I will go back and re-record parts that have mistakes. But in the meantime, best of luck in your astronomy exams. If you need any support, you know where I am. There is a Discord server, Physics with Keith. The links are on my website, physicswithkeith.com, and there's a forum within that server just for astronomy, if you want to ask any questions, get any advice, get any support, that sort of thing. But otherwise, good luck with your coursework, best of luck to you, and let me know how you get on. Bye-bye.